Father, Lord, we just thank you for the opportunity to gather in your name, Lord God. We thank you, Lord, that we thank you for our teacher, Brother Dave, Lord God, for preparing all this coursework, Lord God, for us, Lord. We thank you for the college, Legacy Ministry College, and all the work that they're doing, Lord God, to train up ministers, Lord God, to go forth and do your work. Lord, we just pray, Lord God, that you bless our lesson tonight, Lord God. Let us all glean from it, Lord God, everything that you'd have us to understand, Lord God, that we would be, Lord, prepared to be apologists, Lord God, and prepared to make a defense to the faith, Lord God. Father, we just pray, Lord God, over the technology, Lord God, that it would flow smoothly, Lord God. Father, and we just pray that you bless our time together, Lord God. Bless the video, bless the students that are taking this class, Lord. In Jesus' name we pray.
Amen.
Amen.
Okay, last time we went over the physics stuff, so I just want to do a little review. These are the chapter review questions at the end of the chapter, and this is what Jared is putting together the test from. Okay, so number one, why is Newton often considered the greatest scientist of all time, even ahead of Einstein? Number two, the difference between kinetic and potential energy. Number three, what's the first law of thermodynamics? Number four, what is the second law of thermodynamics? Number five, what does it mean to say a frame of reference? Number six, what do you mean by two-dimensional motion? This is all physics stuff. Number seven, the difference between a balanced and unbalanced force. Number eight, a lot of people misunderstand this. What is a rocket engine pushing against? And people think, well, a rocket can't fly in space because there's no atmosphere to push against. Number nine, conservation of angular momentum displayed by the Earth and Moon system has a very important thing to catch our attention for regarding the age of the Earth and the age of the Moon. Number 10, I have this reversed. It should say, why do heavier objects often fall faster on the Earth and lighter ones do? So I've got it backwards. And I've already fixed that online in the materials, so I'll have to fix this too. Number 11, what would happen if you dropped a sack of concrete and a sheet of paper side by side on the moon? Number 12, how does sound get from a speaker, a loudspeaker, to your ear? Number 13, how do the molecules of water move in a wave on a lake? Number 14, the relationship between speed, frequency, and wavelength. Number 15, what happens to the speed of light when it gets from a less dense to a denser medium, that is, from air to water or something like that. Number 16, the common memory aid to remember the colors of the rainbow. Number 17, why are gamma rays and X-rays so dangerous to living things? Number 18, what does the wave nature of matter have to do with the Bible? Number 19, what's the Doppler effect? Number 20, since you can't get more energy out of a simple machine than what you put in, what's the advantage of using one? Number 21, why does lightning exist? Number 22, why do we hear thunder when lightning strikes? The angels are bowling, right? Why do electrons not have to go all the way around the circuit to carry electrical energy? And number 24, other than photoelectricity and batteries, almost every other form of electric generation relies on what? Okay, you ready for a second? No, let's go over here. Okay, why is Newton often considered the greatest scientist of all time, even ahead of Einstein? It's because Einstein was purely theoretical. Newton was both theoretical and practical. He did a tremendous number of experiments. That's how he came up with this law of gravity, law of conservation of momentum, first law, second law, third law of motion, by experimentation. So, it's great to have somebody do theory, but I think it's even better to do both theory and practice. The difference between kinetic and potential energy, well, when you spin around, you're always moving, right? Stupid memory aid. Kinetic has to do with motion. If something is in motion, then it has kinetic energy compared to something else. So right now, do you have kinetic energy? Compared to what? Compared to your chair? Nope. Compared to an asteroid out in space that sees you moving at thousands of miles an hour, you got a lot of kinetic energy. So when the asteroid hits you, it's going to damage you, but you're going to damage it too. Maybe not as much, because asteroids are a lot tougher than human bodies. Potential energy has to do with position. So right now, if I say, do you have any potential energy compared to what? You're sitting in the chair, you say none, but if somebody pulls a chair out from under you, you fall down because you have gravitational potential energy. Energy is always as compared to something. Motion is always as compared to something. The first law of thermodynamics, the two most well demonstrated, if anything is proved in science, is the laws of thermodynamics. As I always tell people, the only thing that's absolutely proven in science is that nothing is absolutely proven in science. But these come awfully close. Nobody's ever seen an exception of these over the centuries. The first law of thermodynamics says that energy cannot be created or destroyed by any known process. Must be some unknown process. So when you think about the beginning of the universe, well, it had to be an unknown process. Some people say an unknown natural process. Fine if they want to believe that. I believe in an unknown supernatural process. I can't prove it, and I'm not going to try, because it just makes sense to me. The second law of thermodynamics, this is obvious to anybody. You don't hit a pothole and knock your front end into alignment, do you? Energy tends to flow from greater to lesser concentration. It becomes more randomly distributed and less useful. Well, this also has to do with structure. There's stored chemical potential energy, elastic potential energy, magnetic potential energy in things, and as time goes on, they get messed up, and they get less organized. So you hit that pothole, and oops, what used to be a nice bit of stored potential energy in the shape of your automobile, it just got crooked, and it's not going to come back to the way it was by itself. So this one is what we're going to go back over in a few minutes when we restart the chapter. The universe has a built-in tendency toward deterioration. It's not that the energy is going to go out of existence, it's that it's going to become less and less useful. It's going to spread out. And I was taking a chemistry class for teachers one time, and the professor, who's a friend of mine on my master's committee, he said, we don't understand why, but absolutely everything that ever happens increases the entropy, the disorganization of the universe. And I was thinking, I do understand why, because the Bible says all of creation is in bondage to decay. What does frame of reference mean? Well, it's a position where you can measure motion against something. So if you go to a football game, you could get your seats on a 50-yard line and say, okay, they're 50 yards that way, okay, they're right in front of me to 0, 50 yards that way. Or you could say, let me get in that end zone, there's 100 yards away from me. Or we could say, let me get in that end zone, well, here's 0, and then that's 100 yards. You can pick any frame of reference you want as long as your mathematics are consistent. They're all, as long as it's not accelerating, they're all equally valid to describe motion. Two-dimensional motion is a whole lot more commonly analyzed than one-dimensional motion. One dimension is a straight line. Speeds up, slows down, stops, goes backwards. The two-dimension, it also goes up and down, left, right, something like that. And of course, three-dimensional motion, then you have to worry about all three directions. You have height, length, and depth, three dimensions, X, Y, and Z. The difference between the balanced and an unbalanced force is that a balanced force is canceled out by an opposing force. I notice you're not all falling. Why not? The force of gravity pulling down on you ought to be making you fall. But you're not falling because what? Because there's an upward force, a balancing force exerted by your chair. If there were no balancing force, then yeah, you would certainly start to move in accordance with Newton's second law of motion. That's what we're going to make. Force applied to a mass is going to cause an acceleration. In space, what is a rocket engine pushing against? It's not pushing against the atmosphere. The rocket engine is burning fuel. So the fuel is trying to expand every which way, and it's pushing all around, including on the front of the engine. And the engine is pushing back, including on the front. But at the back, there's nothing there to push back against the fuel. So the rocket engine is pushing against the fuel, the expanding fuel. and the expanding fuel is pushing against the rocket. So the fuel goes that way and the rocket goes that way. The conservation of angular momentum, which I mentioned last time, the moon is gradually moving away from the Earth, very, very slowly, a couple of inches a year. And to people that say, we never went to the moon, I'm sorry, we'll have shiny stuff up there. That's how we know how far away the moon is. We shine a laser beam, and at the known speed of light, we say, it's 2 inches further than it was last year. So sorry for those that are conspiracy theorists. Yes, we really did go up there. And so the moon is gradually moving away. And that means if you work backwards through time, this is a result of the tides dragging on the moon and the moon pulling on the tides. So if you work backwards through time, the Earth is supposed to be about 4.5 billion years old, but at the present rate of recession, it would have been scraping the surface of the Earth about 1.5 billion years ago. And that's assuming that it's never been any faster, but at the beginning it would have been faster. That's how math works out. I got it right there. Why do heavier objects often, not always, but often fall faster on the Earth than lighter ones do? Because of air resistance. Air resistance is going to depend upon the surface area and the speed. So if you have something that's got a lot of surface area, like a piece of paper, it's going to have a lot of air resistance as it falls. Now, if it's wadded up, then it's going to have less air resistance, even though it's lighter. So what would happen if you would drop a sack of concrete and a sheet of paper side by side on the moon? There's no air resistance there, they fall at the same rate. How does sound travel from a loudspeaker to your ear? It's not that the molecules coming out of my mouth go across the room and go in your ear. That would be really disgusting. But the air hits the next molecule, it hits the next, it hits the next, it hits the next, it hits the next, all the way across the room. How do the molecules of water move in a lake? Now, of course, if there's a strong wind, stuff is gradually going to get blown across. But if you go out there on a fairly calm day, just throw out a fishing fork and watch, it's going to just go, I guess it goes up and down, left, right, left, right. It follows a fairly elliptical or even circular path. Combination of transverse and compressional waves. The relationship between speed, frequency, and wavelength is speed is equal frequency times wavelength. So the speed of light is equal to the frequency of light times the wavelength of light. The speed of light depends on the medium it's going through. When it's empty space, it's about 3 times 10 to the 8 meters a second. When light goes through water, it goes a little slower. Through glass, it goes a little slower. But the frequency is determined by the source. That means the wavelength is gradually going to change. And not gradually, but when it gets into a different medium, that's why light can bend the way it does. Because the speed changes and therefore the wavelength changes. You'll ever see that when you're looking at something under the water, like there's a fish down there, you think he's straight ahead, he's actually down there. But the bending of the light makes it look like that. And how's the speed of light compared to the speed of sound? I don't know. Light's about 900,000 times faster than sound. What happens to the speed of light when it goes from less dense to a denser medium, for instance, from air to water? It slows down. There was a really interesting story I read one time. It was a science fiction story called Slow Glass. I don't remember who wrote it. But in it, somebody invented a type of glass where the speed of light slowed down to just a few millimeters per day. And so they invented this glass, and they would take it to places like Hawaii and just put it out there looking at the sunset and the mountains and all of this stuff, and then sell it to people up in Alaska or places like that so they could have their nice view of Hawaii in their house. Well, theoretically it's possible if you could get light to go that slow. Of course, the twist in the plot of that was somebody committed a murder not realizing he was standing in front of slow glass, and so the police just sat there and waited to see who committed the murder. And your old friend Roy G. Biv, red, orange, yellow, green, blue, indigo, violet, those are the colors of the rainbow. You could break it down into other colors, but it's just a convenient memory aid. Gamma rays and X-rays are not good for you. You know, the Incredible Hulk, he was turned into this great super being by gamma rays. No, you're going to be dead. Gamma rays kill you. They don't make you super powerful. These rays have so much energy. Your cells are made out of carbon, nitrogen, hydrogen, oxygen, phosphorus, sulfur, and stuff. And when that energy hits those bonds, they go, and the cell just falls apart, it flies apart, and you get radiation bursts. You know, it's like getting a blowtorch applied to you. It'll kill you in a hurry. How does the way of nature of matter fit with the Bible? This is where we get back to the Bible. Okay, in Hebrews 11:3, it says, through faith we understand that the worlds were framed by the word of God, so that the things which are seen were not made of things which do appear. Matter, which can be seen, is made of waves which cannot be seen. It's all energy. See how energetic I am? Speaking of energy, Nancy gets so much energy from me. Okay, the Doppler effect, it's either you or the wave source is moving. As long as you're getting closer together, it seems to be of a higher frequency than if you're just standing still with respect to each other. And if you move away from it or it moves away from you, it seems to be of a lower frequency that is stretched out wavelength. That's how Doppler radar works when they talk about it on the weather. It's just seeing are the clouds coming at you or are they moving away from you? Is the wavelength stretched out or is it compressed? Okay, you cannot get more energy out of a simple machine like a lever pulley or something like that. Well, what's the point? What's the advantage of using one? You can spread it out over a longer period of time. So you have to do the same total amount of work, that is, same total energy output, if you can do it slower, which is less power. A typical person, if you get on an exercise bike or something like that, you can put out about 500 watts of power for a very short time, and then you get tired. But if you could bring it down to where you only have to do 100 watts, you can go for a long, long, long time. You're doing the same amount of work, putting out the same total amount of energy. It's just easier because you're spreading it out over a longer period of time. And in addition to that, you can gain more force if you're willing to sacrifice distance, or you can gain more distance if you're willing to sacrifice force. Why does lightning happen? Well, the clouds are bumping into each other. They buffet each other, and the other day we went and ate at a Chinese buffet. No, it wasn't Chinese. Buffet that you buffet your stomach with all the food there. Okay, we went and ate at the Golden Corral buffet. Anyway, the clouds buffet each other, and they're transferring electrons back and forth. So after a while, one cloud has way too many electrons. Another cloud has way too few electrons. So the electrons say, hey, I'm going home, and they'll zap across. Or if there's not another cloud nearby, if they're separated, then the cloud that has too many electrons says, I'm going to send somebody down to the ground. Hey, you down there, look out. Has anybody ever been in a structure that was struck by lightning? It was so weird. We were at Lafayette Park one day in one of the shelters, and they have little lightning rods on. But it got struck by lightning, and you could feel your hair stand on end. You were safe because of the lightning rod, but it was such a weird feeling. And when it struck, it was like getting slapped in the head. So anyway, lightning also can occasionally strike from the ground to the cloud. If you have a cloud that's very deficient in electrons, the ground has got a lot of them available, and they'll jump upward. So you can get cloud to cloud, cloud to ground, ground to cloud. And there's even a weird thing called ball lightning or St. Elmo's fire. I've never seen this, but I've heard about it a number of times. Just a glowing ball of electricity, and it eventually dissipates. Okay, so why do we hear thunder when lightning strikes? It's because the angels are bowling? No. It heats up the air super fast. And when you heat something, it tends to expand, and so the air expands so rapidly that it goes kaboom. Why don't electrons have to go all the way around a circuit to carry electrical energy? You figure I put the light switch on, and the electrons are going that way, and they got to go to the other side of the room. No, the electrons, as soon as they start to move, they set up electric and magnetic fields which push the next electron further down, which push the next one, which push the next one, and the energy goes immediately. The electrons may never get very far away from where they started. In a DC circuit, direct current, eventually the electrons will go all the way through, but it might take a long time. AC, probably not. Alternating current, they just spin right where they are. But their motion creates the electric and magnetic fields that sends the energy on. And then, the most common way of generating electricity, other than photoelectric cells and batteries, large-scale power generation, you get something to spin a giant turbine. It can be water coming down from a mountain. It can be wind. It can be steam, and the steam can be produced by burning coal, oil, nuclear power. But you produce steam, and then the steam blows past the turbine and makes it spin, and it's got these giant magnets. This thing is like 2 or 3 stories high, and the giant magnets are spinning past giant coils of wire. Mm-hmm. And moving a magnet past a coil of wire produces electricity. It's a very carefully controlled rate. Has anybody ever paid attention to what comes out of your wall outlet? It's 120 volts. How many hertz? 60 hertz, 60 cycles per second. The generators are designed, they've got the right number of coils of wire and the right number of magnets on them that they're going to put out 60 hertz electricity. So it's not just that there's one coil, it's, 100 coils, 200 coils, something like that. And so you get all of these backward, forward pulses from the generator, and that's what gives you electricity, and you can make your coffee. Okay, so let's see if I can get over here without messing up. Stop. Okay, it seems like it's working. I sure hope. We got to this at the end of the class last week, but this is so important that I want to bring it back out again. There's a quantity or measurement called entropy, which is the disorganization of matter and energy, and particularly of energy. And every single thing that ever happens increases the entropy of the universe. The universe is gradually becoming less and less and less organized. So the second law of thermodynamics tells us that energy tends to flow from a greater to a lesser concentration. It's not always instant and irreversible. You can have a temporary local decrease in entropy, an increase in organization, but there are certain conditions. You have to have a supply of usable energy coming from outside, like you actually just had a little baby. Well, let's give the baby some energy. Let's hook her up to, let's set off an atomic bomb next door. No, it doesn't do any good. Wrong kind of energy. It's got to be the right kind of energy. And then you've got to have a conversion mechanism to put the energy to a useful form. For example, the baby has a digestive system. And there has to be pre-existing information to guide how that energy is applied to cause organization. Well, the baby has DNA. If there's no DNA, you can throw all the energy you want at it. It's not going to become more organized. And I pointed out also that some people on the evolution side misunderstand. They say, well, things obviously can become more orderly by themselves. For instance, when water freezes and turns into ice, that's a decrease of entropy. No, it's not. Not for the universe. The universe is paying for all of this. Water has always got a structure where you've got an oxygen molecule with 2 hydrogen, well, an oxygen ion, but 2 hydrogen ions attached to it like a Mickey Mouse ears arrangement. That's the structure of water, period. This has been confirmed by X-ray crystallography. It was predicted, and yep, that's the way it is. So if I have a water molecule, there's a positive end sticking out over here and a negative end sticking out over here. But normally the water molecules are bumping up against each other as they move, and they can't stick together. But if you slow them down enough, you cool them off, that is, take the energy out and put it into the rest of the universe, then they can link up. So the energy goes out into the universe, which increases the entropy of the universe. So then they will link up and they'll form ice crystals. And I showed you guys this last time. If you take a sequence of letters and just randomly put them together, it doesn't mean a thing. We put some order on it, put them in alphabetical order, it still doesn't mean anything. But if we convey information, those are exactly the same letters. There's a difference between order and information. DNA contains an unbelievable amount of information. So if we want to have a decrease in entropy, we're going to have to be able to put in a supply of usable energy, has to be a conversion mechanism, there has to be pre-existing information, and the universe has to pay for it. Something has to pay for it. As the entropy decreases in this little local area, it has to increase elsewhere at the source of the energy. So if there was a big bang, it would have been the most disorganized explosion of all time. And for things to become more organized, it's going to have to become more disorganized than being already at its maximum disorganization. It doesn't work. Okay, so somebody was saying about things changing into different compounds and so forth. The ancient people were interested in turning cheap stuff into expensive stuff. The alchemists, so they're trying to turn just dirt and things like that into gold. So there's a distinction between elements, compounds, and mixtures. Elements are things you find on the periodic table. There are 90 of them known to occur in nature. And this is really nice. You can get that on Wikimedia Commons. Just go in there and search for periodic table. There are several of them. This is a basic one, but I'm going to show you later a much more detailed one. It gives you some of the very useful measures. Okay, there are presently 90 elements known to occur in nature, and an additional 28 that have been manufactured in the laboratory. What you do is you take a pre-existing element and you put it in something called a particle accelerator, and you smash it together. Smack. I'm trying to get the thing down. There we go. Smash it together. So we take, say, uranium with its 92, however many protons it has, and we smack a helium nucleus into it at extremely high energy, and if you hit it energetically enough, you can have the other thing stick on. So now instead of 92 protons, you have 94 protons. You can do it again and again and again. The highest we've been able to get is up to atomic number 118. I think that's as far as we're ever going to be able to go, because a little later we're going to talk about electron energy levels. There seem to be 7 shells of energy levels, and by the time you get over here, they're full. And there does not seem to be an 8th shell that you could attach to an atom. We're going to get back to the shells a little bit later. So a compound, as compared to an element, is not found on the periodic table. These are individual elements, scandium, titanium, vanadium, chromium, and so forth. Individual elements, each atom is identified by a certain number of protons. So its atomic number that you see up there, 21, guess how many protons scandium has? 21. Bohrium, 107. Oh, okay. Bohr is one of my heroes, Niels Bohr. Last week, I think I showed you guys a quote from him, or maybe it'll be back up this week. He was a Danish guy, and he said, if you think you understand quantum mechanics, you don't. Everything that we call real is made of things that cannot be called real, which is the same thing Hebrews 11:3 is saying. The things that do appear are made of things which do not appear. So an element, the way we tell the difference between an element, a compound, and a mixture is we try to break it apart. You cannot separate an element into anything simpler short of putting it through a nuclear process. An atomic bomb, okay, yeah, you're going to have the uranium split into barium and krypton perhaps, or something else like that. But short of a nuclear process, you can't change the number of protons in its nucleus. A compound is a little different. It consists of two or more elements combined in a fixed ratio. If it's not a fixed ratio, like we just say, okay, put some iron, put some carbon in there, that's not a compound. It may be something called an alloy. You've probably heard of that, like bronze is an alloy of copper and tin. How much copper, how much tin? Varying amounts, and an experienced metal worker will know, okay, if I put a little more tin, it's going to be a little harder. If I put a little more copper, it's going to have a better sound for a bell or something like that. But there's not a specific formula for bronze, whereas there is a specific formula for water, carbon dioxide, carbon monoxide, methane, ethane, ammonia, things like that. So you can separate a compound into simpler components by chemical means. Chemical means would be things like putting in acids or applying electricity. Why is electricity a chemical means? Because everything's held together by electrons. So when you apply electricity, you're doing a chemical thing to something, and you can break it apart. That's how we get aluminum out of the ground. It used to be that aluminum was extremely rare and extremely valuable, and sometimes kings would give other kings blocks of aluminum. But then, when we discovered how to produce electricity of high currents, it's pretty easy to get aluminum out of the ore in the ground, out of bauxite. It's a chemical process. Bauxite ore has got aluminum and other stuff. You apply the electricity, there comes the aluminum. So if the formula changes, it becomes a different compound or element. So for instance, with hydrogen and water, H2O, how can you break those apart? Simple, electricity. You apply a little bit of electricity to it, or direct current, and you can separate the hydrogen and oxygen. And you collect them, and it's really cool if you, on the negative terminal, you're going to get the hydrogen, on the positive terminal, you're going to get the oxygen. You collect those gases, then you allow them to mix together, and you put a little spark in there, and you're going to get the most satisfying bang if you ever want to hear. Oh, they explode very, very rapidly. You heard of the Hindenburg balloon? It didn't really blow up. It burned. And actually what started that fire seemed to be a lightning strike against the aluminum skin, and the aluminum is what caught fire. If the hydrogen inside of it had reacted with oxygen, it wouldn't have burned gradually. It would have gone kablooey all at once. Okay, so you can separate a compound by chemical means such as acids or electricity, but then are you an element? Are you a compound? You're a mixture. Everything else is a mixture. It's a collection of elements and compounds that doesn't have a definite formula. For instance, salt water. What's the formula for salt water? Some salt and some water. What's the formula for coffee? Put some coffee in it. There's no definite formula. It's not like coffee 3H2O4. So everything else is going to be a mixture. And a compound has properties that are different from the elements that make it up, almost always different. For instance, if I take hydrogen, which is a clear gas, lighter than air, much lighter than air, and I mix it with oxygen, and I give it a little spark, and it goes kablooey and comes together. Whoa, now it's a liquid. Now it's much heavier than air. The properties of the compound are much different than the properties of the elements that put it together. And another example, table salt. If you sprinkle on your French fries, sodium, the formula is NaCl. Sodium is an explosive soft metal. Throw it in water, it goes bam! But yet, you put it on your French fries once it's combined with chlorine, and chlorine is a deadly, poisonous green gas. Whenever there's a train derailment, and they had a tank car full of chlorine, everybody gets so worried. But you put it together with sodium, and that's salt, and you eat that. So the properties are very much different when it's in a compound than when it was separate. So you can separate a compound by chemical means, such as electricity, acids, and things like that. Most things are mixtures. You don't have a definite formula, you're a mixture. Your blood is a mixture. It has red blood cells, white blood cells, all of the different things in there. Your cells are a mixture. You can have two different kinds of mixtures. One is called homogeneous, that is the same throughout, and you've heard of homogenized milk, right?
Mm-hmm.
Okay. When milk comes out of a cow, it's all lumpy. Anybody ever seen milk right out of a cow? No. It's lumpy. It's got clumps of fat. So they homogenize it. They put it in like a big blender and chop it up. Of course, they also pasteurize it. Anybody know what pasteurizing is? You heat it up enough to kill the bacteria. So what's the fastest thing on earth? Milk. It's pasteurized before you even see it. People that are watching this video say, it's a deal science. Okay, so a homogeneous mixture is the same throughout, even under a light microscope. Now, if you put something under an electron microscope, magnifying hundreds of thousands of times, you can see a difference. But a homogeneous mixture, like sugar water, you can't see the individual molecules of sugar in that, even under a good quality light microscope. Electron microscope, yeah, you could. So that's generally the standard to be able to tell the difference. And another way you can do that, if you have a homogeneous mixture, you shine a laser through it. Okay? If you can see the beam of the laser in the liquid, then it's heterogeneous. A homogeneous mixture, the light goes right through and you can't even see it. Maybe we'll do that later on. I'll show you guys. A heterogeneous mixture, hetero means other. So for instance, concrete, there's certainly visible differences in it. You've got little rocks and chunks of this and that. And you've got garden soil, we've got mud and little worm guts and stuff like that. Well, that's a heterogeneous mixture. So you can separate a mixture by physical means. You may be able to reach in there with a pair of tweezers and grab stuff, or you may be able to sift it or boil it. If you want to get all of the trash out of water, what you do is distill it, and what you're doing is boiling off the water, which has a certain temperature at which it vaporizes, and the water goes away, and what's left behind is all the crud. We have a water distiller we use at home, and it's really disgusting to see what's in the bottom of that thing every time you distill water. So that's boiling. And you also could use magnets. You could put something in a centrifuge. It's a spinning thing, and stuff that's denser is going to be thrown to the outside. Stuff that's less dense comes to the inside. So actually, when you're trying to make an atomic bomb, y'all plan to make any atomic bombs? No, okay. If you're trying to make an atomic bomb, there's two isotopes of uranium in the ground. Uranium-238 and uranium-235. 238 is useless for bombs and nuclear power plants and so forth. 235 is the stuff you need. So what you have to do, one of the ways to separate it, is put this in a centrifuge. You vaporize it. So we got uranium vapor. Start to spin it. The 238 is slightly denser. It's going to be thrown to the outside. The 235 is going to collect more toward the inside. And when you gradually cool it and it solidifies, the stuff on the outside is the useless stuff, the 238. The stuff on the inside is the useful stuff, the 235. So you can separate not only mixtures of different elements, even mixtures of a single element. That's one of the techniques that you can do. And then, have you ever wondered how you get liquid nitrogen and liquid oxygen and all of that stuff? Well, you just go someplace and buy it, right? But how do they separate it? The air is about 78% nitrogen, 21% oxygen, 1% other stuff. So you take the air and you put it in your machine with very sophisticated equipment, and you start to cool it down, cool it down, cool it down. And when you get to a certain temperature, all of a sudden you get this white solid stuff, which we call dry ice. It's carbon dioxide, which goes immediately to a solid. Okay, you pull all of that out. Now you've got still a mixture. You cool it more, cool it more, cool it more, and eventually you see one of them turn into a liquid. I don't know which one liquefies first, whether it's oxygen or nitrogen. You get all of that out, and then what's in there, you can just take it as it is or continue to cool it, and get liquid nitrogen, and then the other stuff is in there, and you can get liquid helium and all of the things that are in the atmosphere eventually. It's called fractional distillation. Okay, is this exactly what an atom is like? No. Remember, if you talk about a law of nature, you're saying this is what always happens, you've never seen an exception. If you talk about a scientific theory, this is your explanation for why something happened, and you've tested it over and over again, and you've never seen an exception. So for instance, we talk about cell theory in biology. That theory is a proposed explanation for why living things behave the way they do, and it says, for one thing, that every living thing is composed of cells. For another thing, that cells only come from previously existing cells, and I don't remember what the other part was. What would it take to disprove cell theory? Find any living thing that's not made out of cells. So it's been tested ever since Leeuwenhoek first observed the first cells back hundreds of years ago, and nobody's ever seen anything that's not composed of cells. So it's a good theory. It's never failed to test. Oh, and it also enables you to make predictions about what you're going to find in the future. So, can we do that with atoms? You can see cells under a microscope. Can you see the details of an atom under a microscope? Even under the best microscopes we have, scanning tunneling microscopes, you can see the blurred outline of an atom, but you can't see the details. It's just too small. So, since you can't actually see it, what we do is put together the knowledge that's available to us into something that's called a model. So this is very commonly used, a planetary model of the atom. Nobody believes this is exactly right. It just helps you to get a picture of what's where. So in the center of the atom, you have a nucleus, which is composed of protons and neutrons. And then somewhere moving around are electrons. We used to say they were in orbits, now we say they're in orbitals. We'll get to that a little later. So the number of protons determines the atomic number, and that determines what element it is. So the protons attract a specific number of electrons. The number of neutrons keep the protons from flying apart. The electrons are about 1/1836th the mass of a proton. They're about 1/1837th the mass of a neutron. So a neutron is heavier than a proton by about the mass of an electron. Okay, so when we put together the number of protons plus the number of neutrons, that's called the mass number or the isotope number. I mentioned a few minutes ago uranium-235 and uranium-238. So uranium has 92 protons, so subtract that from 235, that tells you the number of neutrons in the less stable isotope. Subtract it from 238, that tells you the number of neutrons in the more stable isotope. Okay, as compared to atoms, we don't have a complete picture of the atom, but we think we have a pretty good idea. Remember, I showed you guys about the blind men of Hindustan. They encountered an elephant in the jungle, and one of them bumped into the leg and said, oh, an elephant's like a tree. Another one encountered the tail, said it's like a rope. That's what we have to do with atoms, because we can't see them. They're too small. Well, with molecules, sometimes we can see them because they can be composed of thousands of atoms. But a molecule is a complete self-contained unit, and it has a definite boundary. So there's a water molecule. It's got an oxygen atom at the center, and two hydrogen, an oxygen ion and two hydrogen ions stuck on there like Mickey Mouse is. That's it. That is a water molecule. So most molecules are the smallest particles of a compound that have all the properties of that compound. So if you apply electricity and you separate the molecule into its components, it's not the same chemical anymore. So for instance, water is H2O. We separate it, now we've got hydrogen and we've got oxygen, and we don't have water anymore. The properties of those gases are completely different from water. Okay, so in general, a molecule is the smallest particle of a compound. However, there's a weird thing, 7 elements on the periodic table that are either gases at room temperature or immediately turn into gases. They can't exist as a single atom. We don't know why, but they don't. So they're up at the upper right corner of the periodic table. It's like a rotated letter L. Now, hydrogen stuck over there by itself. It's one of those that doesn't exist as just a single atom. Hydrogen is in the form of H2. Likewise, over on the right side of the periodic table, nitrogen, oxygen, fluorine, bromine, and iodine, those are the other 6. We don't understand why they don't like being individual atoms, but they don't. So they're called diatomic molecules. So those also are represented, they're the simplest naturally occurring form of that element. So H2, N2, CO2, O2, F2, and so now when they're in a compound though, there don't have to be 2 of them. For instance, in H2O, we only have 1 O. Separate it, and you're going to get some H2 and some O2. Okay, and then I'm going to muddy things up even more. There are a lot of things that are not molecules. They're called formula units. For instance, here in South Louisiana, we have salt domes. The formula for salt is NaCl. Does that mean that's it? It's 1 Na and 1 Cl? No, it goes on and 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 on. So it could form a crystal that could go on just as far as you want. There are some of these that are like thousands of meters long and wide and high. So what we do in order to make it easier to figure out how to put them together, we just say what's the lowest whole number ratio. For every Cl, there's 1 Na. So we write NaCl. It's not a complete molecule. It's part of a crystal. So a formula unit has to do with crystals that are made of negative and positive ions. Okay, and then here's another thing. In chemistry, we use the word substance differently than we do in ordinary conversation. Regular conversation, when you say substance, you just mean stuff, right? Well, in chemistry, when you mean stuff, you say material. But if you're talking about a substance has a definite formula. There are 2 types of things that have definite formulas. One is elements. You get their formula right off the periodic table. The other is compounds. They have a very specific formula. Carbon dioxide is CO2. Sulfuric acid is H2SO4. Definite formula for a compound. So it can be an element or it can be a compound, but it's got to have a definite formula in order to be considered a substance. Otherwise, it's a mixture. Okay? Moving along through chemistry. We're getting there fast. Everything has certain physical properties and certain chemical properties. Physical properties would be things like color, size, shape, hardness, weight. You pick it up in your hand. All you have to do to determine the physical properties is just observe the material. Chemical properties have to do with how a material reacts or doesn't react. So what are the chemical properties of this? I'm going to have to try to get into some chemical reactions to see. So one example would be, if I try to react helium with anything, it ain't going to react. That's a chemical property. If it will react, that's a chemical property. If it won't react, that's also a chemical property. In order to detect chemical properties, you have to at least try to change the chemical formula. You may not succeed. If you don't succeed, you just detected a chemical property. Okay, and then physical and chemical changes. Very similar to physical and chemical properties. Physical changes don't affect the formula. For instance, if I take liquid water and I freeze it, okay, it's still H2O. If I boil it, it's still H2O. The formula is H2O for all of the forms. Formula for forms, okay. So that's a physical change. A chemical change does require a change in the formula. For instance, if I break water down into hydrogen and oxygen, I start out with H2O and I end up with H2 and O2. Well, that's a change of chemical formula, so that's a chemical change. Okay, moving right along. What are the states of matter? Well, in the universe, it's not what we normally think on Earth. I've seen videos where they say the states of matter are solid, liquid, and gas. Well, those are the ones that are most familiar to us. Well, we're made of a lot of solids, a lot of liquids, and some of us have a lot of gas. But you didn't hear me say that, did you? A solid is something where the particles are moving slow enough to link up with each other, and there's a definite volume and a definite shape. In a liquid, the particles are able to move a bit faster so they can kind of slide past each other, but there's still enough attraction that they don't go shooting off into the air. Liquids have a definite volume and they take the shape of their container. In a gas, the particles are moving fast enough that they break their attraction to each other and they can go flying away. So a gas is going to occupy the volume of whatever container it's in if it's a closed container. If it's an open container, it's just going to mix in with the gases in the atmosphere. Okay, those are the three familiar ones, solid, liquid, gas. But then, the most common state of matter in the universe, most people don't think about this, is called a plasma. This is where you've applied enough energy to atoms to remove some or all of the electrons. So it's a bunch of nuclei zipping around, maybe with some of the electrons attached, but they behave a lot like a super, super, super hot gas. If you've heard of a plasma stream TV, you apply enough electrical energy to move the electrons off of the atoms, and it turns it into a plasma. And let's see if this will work. Okay. I hope this will come across on the video. If you're on the video, maybe you can't see it, but this is called a plasma globe. There's a little transformer inside there, and there are wavy little filaments of plasma. This is about a 900 volt power supply on the inside. It's extremely low current. That's why it's not dangerous. It's very high voltage. And so the gas inside there, I believe, is probably argon that's very frequently used. Okay. Can you see this? Yeah, mine. Yeah, there's a little bit coming across. It's plasma going around. And it follows the hand. And I used to love to drive people nuts with it. I have a high frequency hearing loss, so I can't hear it, but if you put a coin up top of it with your finger on, tell me if you all hear high frequency. Yes, no? You don't hear it? Okay, well, never mind. But I used to love to drive my students crazy with that, because I couldn't hear it. So this is a plasma. It's what happens when you apply a very high electric potential, or ultraviolet gamma rays, or something like that, and you strip away some or all of the electrons, it turns into a plasma. The reason I say this is the most common state of matter in the universe is that's what started in the matter. They're so hot that it's just a whole bunch of stuff just running around like crazy. And then there are two more. Back in the 1920s, there was a physicist from India, a guy named Bose, who predicted, this is about the time that we had discovered quantum mechanics, that everything has a wave nature. So he predicted if you could get something close enough to absolute zero, like a gas or something like that, its particle nature would disappear and it would manifest itself as waves. So this was an interesting idea to Einstein. He said, hey, put my name on that too. So they predicted a Bose-Einstein condensate. Nobody ever actually was able to make one until about 1995. When I went to the American Association of Physics Teachers meeting in Salt Lake right before Hurricane Katrina, we had 3 Nobel Prize winners speaking to us, one of whom was the guy that had made the first Bose-Einstein condensate. So you have to get something very close to absolute zero. That means it has to pretty much stop moving. Well, are you moving? Compared to what? Compared to the laboratory where they were doing the work, they had to get it to stop moving. So they fixed up an array of thousands of lasers, and they sprayed some vapor in there. I don't know if it's iron vapor, but some kind of vapor, and they turned on the laser. If one laser hits one atom, it's going to knock it that way. But then if another laser hits it, and it's going to knock it back. And another one hits it, and the atoms just floating around, vaporized atoms, are going to go. And eventually they can't go anywhere because the lasers are holding them in place. And lo and behold, they got a Bose-Einstein condensate. So it was theorized and it came to be. It's not something you or I are very likely to see because it requires conditions close to absolute zero. But yeah, it was a successful prediction of, I don't know what you call the theory, some kind of chemical theory. And then there's yet another state of matter. It's called a quark soup. What's the simplest particles of matter? For practical purposes, protons, neutrons, and electrons. However, scientists have put these things into particle accelerators and smack them together at close to the speed of light, and they break down into smaller particles called quarks. So far, they've discovered 6 varieties or 6 flavors of quarks, and they're of no practical use. But still, protons, neutrons, and electrons are made of smaller particles, and it's all made out of waves anyway. It's also called a quark-gluon plasma. This would occur at energies so high that the protons and neutrons break down into simpler components that are called quarks. It's believed to have been formed several times in super colliders, like the CERN, CERN over in Europe, I think in Switzerland. Well, it's not anything practical, but it's just somebody said, I want to know. Why did you climb that mountain? Because it was there. Why did you want to find out that? Because it was there. Okay, so they've only persisted for a fraction of a second. That's some basic stuff about chemistry. Now let's get to the periodic table. This is a wonderful periodic table if you can get on Wikimedia Commons. And I don't know who CC is, but when you put it on Wikimedia Commons, you're giving people permission to reproduce it at no charge. So whoever you are, thank you very much. This is a great periodic table. It shows the atomic weight or atomic mass. In physics, we make a distinction between weight and mass. In chemistry, we just call it all the same thing. It shows the atomic number. It shows a measure called electronegativity that lets you predict how these things are going to get into a chemical reaction. The chemical symbol, the name of it. It shows the electron configuration. This is a great periodic table. So anyway, if anybody's interested in chemistry, just go download it. It's on the material that I've uploaded to creationrevolution.net. It's also on the Legacy Ministry College Moodle. Okay, so this lets you make a whole lot of predictions. The periodic table is divided into regions. Most of the elements are metals. Up until the stair step, everything to the left of that is a metal. The ones along the stair step, those are called metalloids. They have some characteristics of metals, some of non-metals. And the ones on the right side are called non-metals. Some characteristics of metals is that they tend to be good conductors of heat and electricity, whereas non-metals tend to be poor conductors of heat and electricity. Metalloids, they're controllable. So when you want to use some kind of an electronic circuit, you're probably going to have silicon or germanium in it. We can control the flow of electricity through those by applying bias voltages to them. So they're really, really useful in electronic circuitry. There's a measure on there called electronegativity, and that shows the relative strength of this element in attracting electrons in a chemical reaction. The same guy that got a Nobel Prize for discovering the health benefits of vitamin C, Linus Pauling, I believe he's the one that put together the electronegativity chart. So he ranked the elements on a scale of 0 to 4 for how strongly do they attract electrons. The ones on the left side in group 1 and 2, they have a very low electronegativity, considerably less than 1. The one that's the lowest, I believe, is francium. It just doesn't hold its electron at all. If I'm an atom, I want to have 8 valence electrons. We're going to get back to valence electrons later. Most atoms want to have 8 electrons around the outer edge. So let's say, I'll do my head will be. So let's say I have 7. I want 1 more. If I get 1 more, it's going to be slightly larger. It'll be even bigger. So it's easier for me to get a complete set of 8 electrons by taking one. But if there's another atom that's got an inner set of electrons plus 1 electron on the outside, it's easier for it to have a complete outer shell by giving away 1. So those have a low electronegativity, and the ones on the right side have a high electronegativity. Elements on the left side tend to lose electrons in a chemical reaction with those on the right side. Those on the right tend to take electrons. But if you have 2 elements from the right side, neither one can overpower the other one, so they share the electrons. They pull pretty equally. So like if there's some food that Jackie and I are fighting over and we're of equal strength, neither of us can take it away from the other one, so we have to share the food. So they share electrons. They really would like to take them, but they can't. There's no electronegativity shown for the noble gases because they don't get in chemical reactions. Somebody was able to force one of them into a chemical reaction at one time. I don't remember which one. But generally they don't react, so you don't see electronegativity for those. Okay, there have been many discoveries. I've got to fix this page 75. It says SMAPper, it should say smaller. There have been discoveries of even smaller parts, such as quarks, but the ones that we're interested in are protons, neutrons, and electrons. The electrons are the things that allow everything to combine, but the function of the subatomic particles, in the center of the atom we have a nucleus. And the nucleus is composed of protons. Okay, I skipped over that. The element symbol is 1 or 2 letters, which sometimes doesn't sound anything like that element at all. For instance, lead is Pb, sodium is Na. If these have been known since ancient times, we use the ancient name. Sodium is natrum, lead was plumbum. I don't remember what Hg was. It's some sort of a group thing. And then at the very bottom, there are 2 rows going across, starting with cerium to lutetium and thorium to lawrencium. Those actually belong right in there. So this is part of period 6. This is part of period 7. The reason they write it that way is so it'll fit on a piece of paper. Very practical thing. Okay, so before an atom gets into a chemical reaction, it has the same number of protons which are positive and electrons which are negative, so it's electrically neutral. But when it gets into a chemical reaction, it's happy being electrically neutral, but it would be even happier if it could have 8 electrons in its outer shell. That would mean if it needs to take one, okay, it's going to be imbalanced. It's going to have more electrons, a little more negative. If it gives up one, okay, as long as it's happy, then it's going to be a positive charge instead. So the way you predict how an element will react with another one, you look on the electronegativity chart. If there's a very large difference between them, they go from 0 to 4. The highest one is fluorine, which is at 4 electronegativity. So if you put anything on the left side of the periodic table, sodium, lithium, something like that, with fluorine, it's going to react explosively. Or if you put solid sodium with gaseous fluorine, it's going to react violently. So if you want to be able to predict whether it's going to be a violent reaction, just a mild reaction, you look on a chart of electronegativity. So Linus Pauling, the guy that did the vitamin C, he's the one that put together the chart of electronegativity. Thank you, Dr. Pauling. Appreciate that. Okay, the practical function. The number of protons is called the atomic number, and what protons do in an atom is they pull in electrons. That's their main function. The electrons do everything, but the protons will attract a specific number of electrons. And the protons want to fly apart. If I put two positive things together, what do they want to do? Separate. We don't understand why. For some reason, the protons in all of the atoms don't fly apart. Every element in the universe, except for hydrogen, has two or more protons. So we have two pluses together. They want to fly apart. Why don't they? We don't know. But there's something that holds them together. So let's just slap a name on it. We'll call it the strong nuclear force. Scientists have no idea what it is, but nevertheless, all right, we call it the strong nuclear force. What is it? We don't know scientifically, but I think the Bible tells us. Colossians 1:17, he is before all things, and in him all things hold together. King James says all things consist, but it means hold together. Why don't all of the atoms in the universe fly apart? We have no idea who God is. And Jesus, the Son of God, he is the creator, he's the sustainer. How can a man be born in a little manger in Bethlehem, and yet he's the one that holds every atom in the universe together? Well, I don't understand. If you understand it, explain it to me. Okay, so the total number of protons and neutrons. The neutrons are somehow involved in the strong nuclear force. If there's too many neutrons or too few neutrons, it's going to fly apart anyway, and the strong nuclear force doesn't do much good. Then when we add up all of the protons and neutrons, the electrons don't count, they're so light. Add up all the protons and neutrons, we call that the mass number. And there's a scale of atomic masses. Hydrogen is the lightest. It has an atomic mass of about 1 AMU, atomic mass unit. Helium is 4, and all of the other things have varying amounts of atomic mass. So if I've got uranium-235 has this mass, uranium-238 has a different mass. So what we do is we just average them all up. So if you have 5 different forms, isotopes, and we say, okay, these are 10%, these are 15%, these are 27%, we do what's called a weighted average to get the mass that's shown on the periodic table. So not all oxygen atoms are exactly 16 atomic mass units. If you look on there, you see it's 15.99 something, which means a few of them are very slightly less mass than that. And electrons do everything else. The universe is held together, compounds are held together, you're held together by electrons. So the protons attract electrons, neutrons keep protons from flying apart, and the electrons hook everything else together. So you can use the periodic table to predict how things are going to react. Niels Bohr was the first guy, he's one of my heroes, he's the first guy that figured out when you're trying to figure out the arrangement of electrons around an atom, he determined that there are 7 principal energy levels, and these things are arranged in what you would call shells. I had another one of these, I don't know what happened to it, but is an electron a wave or a particle? The answer is yes. The wave is a particle. So this represents an electron moving around the nucleus of an atom. Where exactly is it? I don't know. It's a wave. But then I can have, let's say that represents a whole shell of electrons. Okay. I can also have, I can't fit it in here. I can also have a second shell, third shell, fourth shell, fifth shell, sixth shell. So here's my inner shell, and I've got another shell. I could have 7 of these shells. That represents the 7 principal energy levels possible for an atom. So I've got some inner electrons, and then I've got the outer electron. Just had a nuclear reaction. I've got the outer electrons, which are called the valence electrons. These are the ones that do the chemical reaction. The inner electrons are not involved in this. They're just there to hold everything in place. If anybody understands exactly how it works, then you need to report it to the Nobel Prize Committee so you can get the Nobel Prize. But it works something like that. So the electrons are arranged in shells. You have the closest shell, and then that would be number 1, and then 2, 3, 4, 5, 6, 7. They match up with the periodic table. It has 7 rows going across. Those are called the periods on the periodic table. So when you add up the electrons in the innermost shell, there can only be 2. That's hydrogen and helium. But when you get to the next shell, there can be 8 electrons in that. So the next shell, there can be 8. The next shell, there can be 18. Next shell, 18. Next shell, 32. Next shell, 32, and that's it. That takes us up to 118, which is atomic number 118. So why is it that the numbers are 2, 8, 8, 18, 18, 32, 32? I'm hoping somebody can tell me, because I'll steal your idea, send it to the Nobel Prize Committee. The chemists call those the magic numbers. Why those numbers? Nobody knows. But anyway, those are the numbers. So a periodic table showing electronegativity is also going to hint at something about why the electrons do what they do. The electrons most involved are the valence electrons. So except for the first 5 elements, they don't have enough protons to attract 8 electrons, so they have to settle for 2. But in general, atoms are most stable when they have a complete outer shell with 8 valence electrons. So if they had 8 on the outermost inner shell and 1 extra electron moving around there, they're perfectly happy to give that up. Because then they got 8, a nice complete outer shell. So here I am. I'm going to leave an man with the atom brain again. If here's my almost outermost shell, and it's got 8 valence electrons in it, 8 electrons, not yet valence electrons, and there's 1 more electron moving around here, around the outside, I'm not really holding it that strongly. I'm very happy to let it go, and somebody else takes it. Now, I've got my 8 valence electrons. Now I'm happy. Why do they like 8 so much? Still waiting for somebody to tell me. So I can steal your idea if they like 8. So the electrons most involved in the reactions are the valence electrons, and the elements in group 1, that's the first column, they have 1 valence electron. Group 2 has 2 valence electrons. Group 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, those have varying numbers of valence electrons because they not only have their outer shell, but they have another one that's close to it, right under, and sometimes they act like valence electrons. So it's a lot harder to predict with those. But group 1 has 1, group 2 has 2, group 13 has 3, group 14 has 4, group 15 has 5, 16 has 6, 17 has 7, 18 has 8. So since 18 has 8, that's the noble gases. They say, I'm going to react. I'm happy the way I am. Get away from me, you commoner. I'm noble. Well, you know, the noble gases, they're snooty, they're noble. But those in group 17, they said, man, if I had 1 more electron, I'd be happy. And they're going to try to take electrons away. Fluorine is up at the top on the right-hand side, group 17. Fluorine is the most reactive element that there is. It's going to take electrons from anything it comes in contact with. So if you swallow too much fluorine, it's going to kill you. There was an episode of ER a few years ago, emergency room, where this guy's brought into the emergency room. He's a lab technician, and they bring him in because he spilled something on himself. And I said, what did he spill? He said hydrofluoric acid. I said, how much? I said, about 1 liter. I said, who's your next of kin? I said, what do you mean? I feel fine. But if you get hydrofluoric acid on you, it doesn't really burn your skin badly, but it gets inside your body. It's going through your bloodstream. And those fluorine ions, the fluoride ions, they are going to react with anything from the left side of the periodic table, and calcium's on the left side. They really can't attack your bones, but you know where else in your body calcium is very important besides your bones? Muscles. In order for muscles to contract, they rely upon calcium, so the fluorine is going through your bloodstream and it says, I'm going to take some calcium away from this muscle, this heart over here, and the heart stops. So they tell this guy, you're going to be dead by tomorrow. Once it's in your bloodstream, you can't get it out. So if somebody ever gets into a chemistry lab class, high school, you will never, ever, ever fool with hydrofluoric acid. If you're in college working with it, you never sit down, and you always wear a lab coat, because if it spills on you, you quickly take the lab coat off, and you don't have the possibility of the stuff spilling in your lap when you stand up. It's very dangerous stuff, because fluorine is such a reactive element. Of course, the second most reactive element, as far as taking away electrons, is, anybody have an idea what? Oxygen. That's why oxygen causes rust. If it were not, we're going to get to this next week, if it were not for the presence of our DNA, we would be in trouble with all the oxygen in the atmosphere. It's so reactive it'll stop all of the other reactions, except the DNA forces it to do the right thing. Okay, so metals tend to give up electrons, non-metals tend to take or share them, and the metalloids, they tend to share also. So if the atom can't attract the electrons strongly enough to take them, it'll say, all right, let's share. So let's say I have 6 valence electrons and you have 6 valence electrons. You're going to hold on to 2 of mine, I'm going to hold on to 2 of yours. So between the 2 of us, we're sharing, and we each feel like we have 8 valence electrons. So that happens in compounds made out of things from the right end of the periodic table. Okay, well, I'm going through just some basic chemistry concepts. You're getting a semester-long chemistry course in 1 or 2 evenings. When electrons are attracted between one atom and another atom, they're going to form chemical bonds. If the difference in electron negativity is greater than about 1.7 on the periodic table with the electron negativity, that's enough of a difference that one atom is just going to take away the electron. If it's between about 0.4 to 1.7, one of them's going to try to take away the electron, but it can't quite get it all the way away, so it's going to pull it strongly toward itself, and this is going to be a polar chemical bond. So I guess the polar bears are familiar with this sort of thing. If there's less than about 0.4 difference in electronegativity on that electronegativity chart, then the electrons are shared equally. Okay, so if I have a large difference in electronegativity, I'm going to get crystals. Salt, sodium chloride is a crystal. But if I have a very small difference in electronegativity, like carbon monoxide, carbon, or something with nitrogen, then it's going to tend to form a molecule rather than a crystal. So water, H2O, the electronegativity of hydrogen and oxygen are close enough that they don't form a crystal. The oxygen pulls the electron strongly, but it can't take it all the way away from the hydrogen, so the hydrogen is still there. But its electron is pulled over to that side, so on this end, sticking out, there's a proton, positively charged. That's why water is able to attract so many things, because the electrons went that way, so we've got a positive sticking out. And water is a good solvent because a lot of stuff will be attracted to that part that's sticking out. Okay, and then everything has got a chemical formula. The formula of an element is a simple symbol from the periodic table. And for a compound, then it's going to be at least 2 elements. You write the symbol of all of the elements that make it up, along with subscripts to indicate how many of these, like hydrogen and oxygen, it's H2O because it's 2 hydrogens and 1 oxygen. Carbon dioxide, we have 1 carbon and 2 oxygen. I should have that as a 2 should be down there. I'll fix that. And then, I'm hitting y'all with a bunch of stuff all at once, I know, whole semester long chemistry course in one evening. There are many compounds that include ions that are made up of more than one element. A lot of these things, oxygen reacts with other stuff, and it gets together and it forms a polyatomic ion, poly meaning many. So, generally they're made out of nonmetals. You could have sulfate, SO4, which is a -2 ion, carbonate, CO4, -1 ion, nitrate, NO3, -1 ion, hydroxide. Hydroxide is really common. And then there's also, the only positive polyatomic ion is ammonium. Everybody ever smelled ammonia? Yeah. It's doing chemical reactions inside you. That's why it's so bitter and unpleasant. So a lot of things involve polyatomic ions, especially acids. If you throw something into sulfuric acid, the SO4 is deeply involved in all of the reactions. And then there's something called chemical equations. It's not an equation in that it has an equal sign in it, like in math, but they call it an equation anyway. It shows how substances, that is, elements and compounds, will react to form other substances. You don't get new atoms that didn't exist before, but you get either elements that were not there in their pure form or compounds that were not there in their compounded form. So it doesn't have an equal sign. On the left side, you're going to have the things that are reacting, and the things that are reacting are called reactants. The things that are produced are called products. So the arrow is red, not equals, but yields. This plus this yields that plus that plus that plus that. And then besides the subscripts, which indicate how many atoms of each element, H2O will be subscripts, well, you're also going to have to show the relative amount of each substance. You could consider this as the number of molecules of each, but actually it's the number of moles. Did you know there are moles in chemistry? Yep, there are moles in chemistry. Amadeo Avogadro was the guy that invented the concept of the mole. So I always like to think of avocado, guacamole. So their coefficients, you have 2 of these plus 3 of those, give 5 of those, or something like that. And then the chemical equations are an attempt to show how things happen. So you can't have new things coming into existence or old things going out of existence. You have to have the same number of atoms on the left as you do on the right of each element. Here's some of the common reaction types. There's hundreds, but here's some of the common ones. For instance, I could have hydrogen coming together, 2H2 plus O2. Notice there is a coefficient. So I have 4 hydrogen atoms on the left, 4 hydrogen atoms on the right. And this coefficient applies to both the hydrogen and the oxygen. So I've got 2 oxygens there, 2 oxygens there. It's a very common type of reaction where 2 things come together, 2 or more things. It's a synthesis or combination reaction. It's sometimes called a composition reaction. Going the other way, suppose I want to break down calcium carbonate into calcium oxide and carbon dioxide. That's called a decomposition reaction. So a guy went to the cemetery where he had heard that Beethoven was buried, and when he walked all around, he found the grave. And it's the weirdest thing. There's music playing from down in the grave. So it's going backwards. It's starting with his 9th symphony, 8th symphony, 7th symphony, going backwards. And he goes over to the caretaker of the cemetery and he says, there's a weird thing going on over here. He says, what is that? There's music coming from Beethoven's grave, but it's going backwards. He says, oh yeah, so? Isn't that weird? He says, no, he's decomposing. Anyway, decomposition reaction is the opposite of a synthesis or combination or composition. And then you can sometimes have where one part of the compound will switch out and replace another part. Zinc plus copper sulfate gives you zinc sulfate plus copper. That's a single replacement reaction. So we have a single element going in and a single element coming out. Then you can also have a double replacement. Calcium chloride plus sodium sulfate The calcium and the sodium switch, and that's what you get. You could also have a complete combustion reaction, which is where you have enough oxygen available. And this is a strange thing to think about. Any combustion reaction always produces water. That's how you put a fire out. Well, a combustion reaction is going to involve something that's got hydrogen in it and oxygen, and one of the byproducts is going to be water. Then if you run out of oxygen, like carbon monoxide poisoning, if you don't have enough, you can get an incomplete combustion reaction, where this reacts with oxygen, you run out of oxygen, and you get carbon monoxide, which is very deadly because the carbon monoxide still wants another electron, and it gets in your lungs and it says, hey, give me an electron. And it takes an electron from something and it breaks down other compounds and kills you. Okay, so these are not the only type of chemical reactions. There's hundreds. But there are a lot of others involving acids and bases and neutralization and things like that. You also may have a symbol put above the arrow. That would indicate heat. You can have a little lightning bolt showing electricity. A catalyst is used to speed up a reaction. If you've never heard of a catalyst, that's how farmers keep track of their cows, with a catalyst. A catalyst is used to speed up a reaction many times faster than it would happen on its own. And when you get to talking about biology later on, the most effective catalysts are called enzymes. They're little molecular machines. They speed up reactions billions of times faster. And very often you're going to put the state of matter, solid, liquid, or gas. An up arrow indicates that in your reaction, all of a sudden, oh, look at that, a gas thing bubbling out. Or a down arrow indicates I put together these liquids or gases and so, oh, a solid fell out. It's called a precipitate. And if you ever see a double-headed arrow, that indicates the reaction can go both ways, depending on the circumstances. Like if it's hotter, it goes that way. If it's colder, it goes that way. Okay, so you ready for a test on this? Okay, one more thing before we get into the history of how all of this knowledge came about is the shapes of molecules. There are 8 valence electrons around an atom when it's happiest. But sometimes the electrons came from another atom that's just hanging over right nearby. So if something is just all by itself like a noble gas, it's going to have more or less a round shape. But if there's something that's attached between one atom and, let's say, 2 more atoms, here's a water molecule. The big one is oxygen, the 2 little ones are hydrogen. It's going to have a bent shape because the oxygen started out with 6 valence electrons. It wanted 2 more. It took 1 from this hydrogen, 1 from this hydrogen, but the other 6 that are already there, they don't like being moved around. They don't want to be bullied. So electrons work in pairs. This is something called Lesepper theory, valence shell electron pair repulsion theory. If you've got 8 valence electrons, they want to go in 4 different directions. You got a pair here, a pair there, a pair there, a pair there, and the maximum separation you can get is not up, down, left, right. The maximum separation is 3-dimensional. So I'm going to try to simulate an atom that has 8 valence electrons. 2, 4, 6, 8. We're going to try to separate as far as possible in 3 dimensions, which means they're going to point all over the place. Well, if I had an atom that had 7 valence electrons that got 1 more, okay, there's no choice. It's 2 dimensions. These 2 atoms have got to form a straight line. It's a linear molecule. But if it had 6 valence electrons, it's very likely to form a bent-shaped molecule because there's a pair up at the top on the left, pair at the top on the right. Single electron down here binds to something. Single electron on the other side binds to something. And it forms a bent shape. And you can get all sorts of different combinations depending on how many valence electrons there are in this atom and in this atom and in this atom. So there were some predictions about the shapes these things ought to be, and they've been confirmed. you can send a beam of X-rays through something and it bounces off the crystals. It gives you a pretty good idea of the shape of the crystals. It's called X-ray crystallography. So these shapes have been confirmed. If I have something that's in a straight line, then there's a 180-degree angle between the two parts on the outside. Or if I have something where there's a central atom and three atoms around it, that's going to form a triangle, a trigonal planar. But I also very frequently will have tetrahedral. We have one pair there, one pair there, one pair there, one pair there. They're pointing in different directions to try to get it. I can't twist like this. To try to get as far away as possible from each other. And because of this, the carbon does this all the time. Carbon has 4 valence electrons and things attached to it at every which angle that you can imagine. So because of that, carbon compounds in particular have all sorts of weird shapes. You know, like snowflakes, supposedly. No two have the same shape. I don't know how you know that. You have to look at all of the snowflakes. But carbon compounds can form all sorts of different shapes, and sometimes one carbon compound is a mirror image of another carbon compound, and the shape is almost the same except a mirror image. They call it right-handed and left-handed depending on how light gets polarized going through it. Back in the 1960s, there was a drug company that manufactured a tranquilizer called thalidomide. Anybody ever hear about thalidomide? Okay, well, it was a good tranquilizer, like Prozac, okay? And it worked great. But they didn't realize if a pregnant, it could exist in two forms, and they didn't really carefully control whether it's the right-handed or left-handed. If a pregnant woman took one form of it, everything was fine. If she took the other form, her babies would be born without arms and legs. It caused massive damage to the baby's DNA. So nowadays they say, you know, if you are pregnant or may become pregnant, they go through all of this stuff at the end of the commercial. They learned that from thalidomide. Because just that little difference in shape, where one molecule is a mirror image of the other molecule, that can cause major health problems. Okay, so now where did all of this stuff come from? I gave you this as a present state of our understanding. I guess I should say of our knowledge, but our understanding. Where did this come from? Well, there are some people that think that anybody that believes in God is stupid. You know, most of the great chemists down through the years have been Christians. Or at least they believe in some sort of a God. There have been a lot of Muslims contributing as well. So some of them, like Boyle and Lavoisier and Faraday and Maxwell and Compton and Newton, Dalton, Gauss, J.J. Thomson, Volta, Pascal, Lord Kelvin, Heisenberg, Davy, Eddington, there's just a few, and they were all very, 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 very devout Christians. They were British too. Okay, there was one ancient guy named Democritus. He proposed, it was hundreds of years BC, he proposed that if you cut a piece of something like gold in half, it's still gold. Cut it again, still gold. Cut it in half, it's still gold. He said, you know, logically, if you keep going, you're going to reach a point where if you cut it one time, it's not gold anymore. You can't cut it past that. Well, the Greek syllable for cut is tom. So it was an uncut thing, a non-cuttable, an atom. If anybody has ever had a CT scan or a CAT scan, CT stands for computerized tomography, or CAT is computer axial tomography. And what they're doing is virtually cutting through you. You take a little slice. So the tom indicates cut. Now here's a weird thing that happened some years ago that's nothing to do with that, but had to do with cutting. If a doctor wants to know what's inside of a person's body, of course they get a cadaver in medical school and they dissect the body to see what's in it. But there is also a service a doctor can sign up for. Some years ago, there were 2 executed criminals that agreed to donate their bodies to science. Okay, somebody went to them and said, look, after you die, we would like to dissect your bodies and we'll give the remains a decent burial afterward. Would you allow us to do this? They said, what the heck, I'll be dead. So it was a man and a woman. And when they were executed, they hard froze the bodies and then stood them up and took pictures of the top of the head, camera going around taking thousands of images, shaved off a little bit, took more pictures, shaved off a little bit, took more pictures, went all the way down and got a complete view of the inside of both the male and female body, and a doctor can subscribe to that service. So I don't know what they call the process, but it's similar to computerized tomography, but they actually did do tomography. Okay, so Democritus came up with some ideas. He believed that everything is made out of atoms, and of course there'd have to be an infinite number of atoms to make up all material objects. Now we would say there's about 10 to the 76th power, which is not infinite, but it's a big number. And Democritus said all atoms of the same element have the same shape, but atoms of different elements may have different shapes. So why are they different in taste? They have a different shape. Why are they different in hardness and so forth? He believed solids had little hooks on the side so they could hook together and become solid. Well, he had no way to investigate this thing. He just said it seems like this ought to be. And he said atoms cannot be destroyed, and they're surrounded by empty space, and they're always in motion. Well, that sounds like some pretty reasonable things, except the famous guy Aristotle came along a few years afterward, and Aristotle said, no, I know everything, you have to trust me. Aristotle said it, I believe it, and that settles it. Aristotle said, no, there could not be any such thing as empty space. And because he was the famous guy. Why was he so famous? His student Alexander the Great spread his ideas. So Aristotle said, no, Democritus, I'm sorry, you're wrong. And so Democritus' ideas were thrown on the trash heap for about 2,000 years. That's a shame, because he was pretty much on the right track. So the alchemists were not concerned with theoretical discoveries, but they came up with all sorts of lab techniques that we still use, like the mortar and pestle and crucibles and glassware and experimental techniques and so forth. Yeah, the alchemists, they weren't doing any theoretical stuff. They just want practical results. How do I get gold out of the ground? Okay, so then we go ahead to the 1740s. Antoine Lavoisier. He was a French nobleman, and he was a brilliant chemist. He's considered the father of experimental chemistry. He demonstrated the law of conservation of mass, for instance, by saying, wait, I'm going to do my experiments inside sealed containers. So let's weigh it, get the reaction going, make sure nothing gets in or out. Look at that, the mass is exactly the same actually. Where previously, gases would escape and the mass changed and people thought it went out of existence. So this was really the beginning of the first law of thermodynamics, which involves energy as well as mass. So he showed the law of conservation of mass. He did his experiments inside sealed chambers. He named oxygen. Somebody had to name it? Yeah. He named oxygen. And this guy invented a lens using the sunlight where he could get temperatures hotter than were available in a furnace. Big old lens. And then he also developed a naming system that we use in chemistry today. But if anybody's seen it, plug your ears in about 2 seconds. Lavoisier was an aristocrat during the French Revolution. And in the Reign of Terror in 1794, they said, he was a genius, right? Well, the French word is savant. And as they led him to the guillotine, they said, France has no need of savants. So they put him on the guillotine to cut his head off. And he told his friends, okay, just out of curiosity, I'm going to blink as many times as I can after they cut my head off. So you can see, is there still consciousness? So he blinked for 30 seconds after his head was cut off. It's creepy, isn't it? Anyway, Lavoisier really started experimental chemistry in the 1700s, and then it had been many years since anybody paid attention to Democritus' ideas, but a guy named John Dalton, 2 of the great developments were made by school teachers, not chemists. John Dalton was not actually a chemist, he was a chemistry teacher. Go teachers. He found a way to indirectly test some of Democritus' ideas. he was a contemporary of a guy named Proust, and Proust published something called the law of definite composition or definite proportion. Anytime I reacted this element with this element, there was an optimum ratio between the two of them where I had minimum waste at the end. If I had some other ratio, no, I got a lot of this left over, a lot of that left over. But there seemed to be an ideal ratio. So Dalton developed that, and he said there must be an ideal ratio of atoms of each element in the formation of a compound. This is testable. Democritus had no way to test his ideas, but this was tested. And he published this theory in 1808, just over 200 years ago. And the main features were, okay, A, all matter is made of indivisible atoms. B, all atoms of a given element are identical to each other. And then the next one, two or more atoms can combine in various ways to make compounds, and they will always combine in simple whole number ratios. And the properties of the compound may be very different from the properties of the elements that make it up. And chemical reactions are not as a result of things coming into existence or going out of existence, but simply from atoms being rearranged. Now, this is a theory because it's testable, and two parts of it have been falsified, but it was close enough that we said, okay, let's just modify it instead of throwing it out completely. Remember, Aristotle said everything on earth is made of what? Four things. Everything on earth? Earth, air, fire, water. Well, that's stupid. That's junk. We throw that out. This one is close enough. We said, well, let's kind of keep it, just make some modifications to it. So two of his ideas were later falsified. One of them, he said the atom cannot be subdivided. Well, we found out later, yes, it can. Protons, neutrons, and electrons. But those parts don't have the properties of the original element. And he also said all atoms of the same element are identical. And now we found out, no, there's these things called isotopes. It's the same element, but they're slightly different in mass. They vary depending upon neutrons. So Dalton also, he was, a chemistry teacher, but he did a lot of experimental work. He did a lot of work with gases, and he published something called the law of partial pressures. It says in a mixture of gases, each individual gas furnishes a definite partial pressure contributing to the whole. And this is a really useful thing. Okay, and shortly after Dalton published his theory, there was an Italian physicist, Mr. Amedeo Avogadro. He proposed that equal volumes of gases, take a 2-liter container and fill it with hydrogen, fill it with helium. He said, I think it ought to have the same number of atoms. Yeah, it's been confirmed. So that paved the way for the discovery of relative atomic weight. This guy, you never hear about him, Berzelius. He's the one that he started comparing. He said, okay, let me take a container full of hydrogen. Okay. And I'm going to use that as one. It's going to be my atomic mass one. Now let me take exactly the same size container and fill it with helium. Oh, that has an atomic mass, or it has a mass of 4. So, okay, the relative atomic mass of helium as compared to hydrogen is 4. And he tried oxygen and nitrogen and so forth. And you could also do it with vaporized stuff. You turn it into a vapor and you put it in there. And so he's the one that really first started coming up with those atomic masses that you have on a periodic table. It wasn't as precise as it is nowadays, but it was a pretty good approximation. So he now had atomic masses, and we're going to be to Mendeleev in just a minute. Mendeleev, I don't know how you say it. He developed his new idea, a periodic table of the elements. So Mendeleev was a school teacher, and he became a chemist. By the time he did his work in 1869, there were about 63 elements that were known. So Mendeleev, he was kind of a rascal. His wife was in one part of Russia, his mistress was in another part, and he had to take the train across Siberia. So this is not one of the guys who was a Christian. As he took the train across Siberia, he needed something to pass the time. So he made cards with the properties of the then known elements, 63 of them at the time, and he arranged them according to their atomic weights calculated by guys like Berzelius. And he found that the chemical properties pretty much repeated every so often. And later on, it was rearranged according to atomic numbers rather than mass, because there were a few exceptions where they didn't work out quite right. But he started arranging them left to right, and up. Repetition of properties, let's start over again. Next period down on the periodic table. And he also left blanks for other elements. He said, we're going to have to find something that goes in here that's in between. And he made predictions about 3 new elements that ought to be discovered, and sure enough, it was right. So there was another guy working on his own version of the periodic table at the same time, a fellow named Lothar Meyer. His problem was he wasn't as bold as Mendeleev. Mendeleev made predictions. I think we're going to discover something here. Meyer never made predictions, so he kind of faded away into obscurity. Since Mendeleev's time, we've manufactured or discovered a whole bunch more elements since then. The periodic table has been modified, but it's still recognizable as the same basic design that we came up with. So we've now got a periodic table. It's the late 1800s. And at about the same time, there's a guy named Volta. You heard of volts in the electric outlet? A guy named Volta invented something called the voltaic pile, which was a battery. Nobody had ever had batteries before. So he found out he could stack these things, and he could get just as high a voltage as he wanted. It was all DC voltage. And so other scientists said, hey, that's a great idea. And working with DC voltage, they decided, let's put the gas inside of a container and just attach an electric current to it. Why? Because you want to. That's why. You just feel like it. So the first one that did work like this, or one of the first ones, was Michael Faraday, if you knew anything about electricity. Famous guy in the development of electrical theory. Well, he was running electricity through tubes, and one of the guys that made the most successful design was Crookes, Sir William Crookes. So this is a Crookes tube. I used to have one in my classroom, and it had a gas on the inside at very low pressure. It doesn't work very well at normal atmospheric pressure. It doesn't work if you have a complete vacuum. But somebody said, let me suck some of the gas out. I don't know why they thought of doing that, but they did. So when they did, and they connected a high voltage electric charge, like 900 volts or so, going across here, there was a glow. It went from one end to the other, and so it went from the part that was called the cathode to the part that was called the anode, so it's called a cathode ray. So the glow went along, and people doing experiments with this, they got curious and started doing stuff like waving magnets near it. Light doesn't respond to magnetism. Okay? Pure energy does not respond to magnetism. So here we got this glowing stream of whatever it is inside there. Let's wave a magnet. Oh, look, it's reflected. That indicates it's some kind of particles of matter. All right, well, what is it? Okay, we got our tube with hydrogen in it. Let's try one with helium in it. Same result. Let's try one with nitrogen, oxygen, fluorine. All of them behave the same way. They all had some kind of a particle that got knocked loose from the atoms when you applied a high voltage electric charge. But when you took the electricity away, they're back on their atom. They must be part of the atom that can be separated. Woo! This was the first time anybody realized, okay, there are smaller parts of the atom. So the guy that did the most work on this, he's not the only one, but J.J. Thomson, he is at Cambridge University in England. I'm telling you, there was a whole string of Nobel Prize winners. He taught the next guy, taught the next guy, taught the next guy, and they all got Nobel Prizes all the way down the road. Okay, so J.J. Thomson did experiments with this, and he said, whatever that thing is flowing along to here, it's a part of every element, and he called it corpuscles, and later on there were things too, electrons. So he discovered that they were there, and he did a lot of work on those, and he got a Nobel Prize. And then another guy named Robert Millikan got a Nobel Prize because he was able to calculate the actual charge. All right, so when the atoms are at rest and we don't have the high voltage electric current applied, where are the electrons? Oh no. This guy was British. All of these British guys, they have certain desserts, like they have plum pudding. Plum pudding is actually a raisin pudding, and we would think of it more like a chocolate chip cookie. But he said, okay, when the electrons are not flowing, when the corpuscles are not flowing, where are they? They must just be stuck all around the outside of the atom. There's no way to see this, but it made sense to him. So his student, Ernest Rutherford, he wanted to, suck up to his professor and show that he was right. So he devised an experiment. Now he's teaching. He devised an experiment where he would shoot radioactive particles. Radioactivity was discovered around 1900, and so this guy, Ernest Rutherford, he was aware of 3 different types of radioactivity. In fact, he discovered alpha particles and beta particles. So he got a Nobel Prize too. So he had inside a lead box, he had radium, and it was a little bitty opening like a gun barrel, so he could shoot the particles, and they went through a gold foil. He expected that if his professor's idea was right, then the particles ought to just pretty much go straight through all the time. Because the electrons are so spread out, positive charges so spread out, they should just go right through. But these alpha particles are positively charged. They expected them to go right through. They didn't. Many of them were deflected at significant angles. Some bounced straight back. And he said it was as if you fired a 16-inch shell at something, at a tissue paper, and it bounced off. What? So his idea of confirming what his teacher said turns out to falsify what his teacher said. His new model of the atom said, okay, the positive charges have to be concentrated in a very small center, and the electrons have to be somewhere around the outside. He didn't know exactly what. It's somewhere around the outside. Later on, he realized, okay, this one has more positive charge than that. This has more than that. So he said there's got to be an individual particle, which he named a proton, that's responsible for the positive charge. We still can't see the details of an atom, but by beaming stuff through, he was able to allow scientists to calculate the approximate size for the first time. This is a scanning tunneling microscope image of a single cobalt atom. You can't see the details, can't see protons, neutrons, electrons, but you can see that there's a Bohr. So the new model of the atom says we've got a positively charged nucleus, and the electrons are moving somewhere around the outside. Exactly where? Let's let the next student get to this. Niels Bohr, he studied under Thomson and Rutherford, and he realized, okay, if the electrons are just sitting there, they're negative, the nucleus is positive, they're going to get sucked in. They've got to be moving. He said they must be orbiting. Well, if you analyze the colors of light that come out of things, Bohr came up with an explanation for that. And I don't think this is very boring at all. I think it's very exciting. Bohr said, okay, if this thing, this electron, is at this distance from the nucleus, and it suddenly drops to that distance, where did the energy go up? Where did it go? It came out as a color. Drops here, it came out as another color. If I wanted to go to a higher energy, I have to send in a color. The colors have different amounts of energy. So depending on which of the 7 energy levels the electrons were in, that would account for the colors that you get from hydrogen. We analyzed very carefully the colors of hydrogen. It's the only atom that has a single electron. And he did a perfect job predicting this should be the colors that I get out of hydrogen atoms, or they can absorb the same colors. And Bohr's work was perfect. The wonderful emission lines that when you heat the thing up, it sends out that color. When you cool it down, it absorbs that color. So if we want to know what's in an element, what's in a star, we analyze the light. And we find out what are the emission lines, what are the absorption lines, compare that to what we've done in the laboratory. And we've analyzed all 118 elements in the laboratory. So we can point our telescope at a star, get the light, and say, okay, it's made of this element, this element, this element, this element. That's how we know that most stars are hydrogen and helium, and they have little bitty bits of other things, just from analyzing the light of the star. So when Bohr did this, it did a wonderful job for hydrogen only. Wouldn't work for anything else. And he really started quantum mechanics, and he's a guy that said everything that we consider as real is made out of things that we cannot consider as real. I love this guy. He couldn't explain the colors of any element other than hydrogen. So they had to be not just the principal energy levels, but they had to be energy sublevels. Because like if you look at oxygen, it's got a bunch of lines, much more so than what you would expect from its number of electrons. So there was a guy named Louis de Broglie. He showed that electrons, are they a wave or a particle? Yes. He's the one that showed they're either a wave or a particle depending on what you're doing. And then a guy named Erwin Schrödinger, he derived this equation, and it is incredibly complicated mathematics. It's way beyond me. But if you want to describe the behavior of a real particle, an electron, you can't do it with real numbers. You have to have imaginary numbers. Just like the electron was here, disappeared out of normal space and went to imaginary space and appeared here. The wave equation describes it beautifully. And the wave equation allows you to come up with all of the different colors of light that you're going to get from all of the various kinds of elements. Okay, so Schrödinger derived the wave equation, and that's really the basis of our description of the electron now. Now, this is another guy that I have so much respect for, Werner Heisenberg. He was also a very influential figure in developing quantum mechanics. Tell me exactly where the wave is. You can't. A wave is over here and it's over here. So sometimes these particles behave as particles, sometimes they behave as waves. Heisenberg theoretically developed the uncertainty principle. It's not just we can't measure accurately, it's just the more precisely we try to measure, the more we mess it up. So if you know precisely where something is, then less precisely can you tell where it's going. It was not just due to uncertainty of measurement, but to the wave-particle duality of nature. So when an electron is outside of an atom, it usually behaves like a particle. When it's inside, it behaves like a wave. So this would be, if you picture throbbing in and out, that's our picture of the electron now. It's a throbbing wave. There's a wonderful song, I'm going to try to bring it in next week. It's called the Atom Song, and it says, the atom is a fuzzy blob of pure uncertainty. And here's a really cool thing about Heisenberg. He was German. From what I understand, he was a Lutheran. He didn't like Hitler. He didn't have any choice. He won a Nobel Prize. Hitler said, hey, I want that guy in my program. So Heisenberg was assigned to head up the German nuclear energy program. And he was kind of like, if you ever saw Schindler's List or heard about that? Mm-hmm. Schindler made sure that those artillery shells manufactured in his factory would not work. Deliberately sabotaged. Heisenberg headed the German nuclear energy program trying to develop an atomic bomb. They didn't succeed. After the war, the other German scientists said, yeah, Heisenberg knew how to do it, he wouldn't let us. He didn't want Hitler to have an atomic bomb. And also, Heisenberg discovered the neutron at the same time as a guy named James Chadwick, and Chadwick was put up for the Nobel Prize, and Heisenberg was nominated along with him for his co-discovery of the neutron. He said, I don't want that. I don't want Hitler to know. So he had no choice. He was kind of like drafted into the German scientific corps, but he would not cooperate. So this is a cool guy, in my humble opinion. Okay, and let's see how much time we have left. All right, let's finish up about Chadwick and the neutron. There was a very bashful young man named James Chadwick who enrolled at Cambridge University. All these guys in Cambridge. And he went in mathematics, and when he did, they made a mistake and they put him in physics, and he was too shy to complain, so he said, all right, I'll take physics. Well, he wound up working in the same lab as Thompson and Rutherford and Bohr and, all of these guys. So, in day-to-day chemistry, protons, neutrons, and electrons are much more practical than quarks. But James Chadwick, by now we have discovered the the electron and the proton. But James Chadwick said there's got to be something else. The masses of these atoms don't match up. So he began to do experiments using very low-tech stuff, paraffin wax and alpha particles and stuff like that. And we discovered, okay, here's this other particle, the neutron, and so he got a Nobel Prize for it. Other scientists immediately began to use his discovery of the neutron to split atoms, and Chadwick realized, oh my God, I opened the door for nuclear bombs. Very shy young man. He said from that point on, he had to take sleeping pills for the rest of his life just to see. Because he knew, because of his work, the atomic bomb was not only possible, but it was inevitable. So he was one of the British guys who was brought in to work on the Manhattan Project. It was in the Manhattan district of the Army Corps of Engineers, that's why they called it that. But they were the ones that were tasked with developing the atomic bomb in World War II, and he was one of the chief scientists on it, along with Oppenheimer, who headed the project, and Leslie Groves was the military guy in charge. He had to make sure it worked. But Oppenheimer directed it, and there's Chadwick with him. Einstein was not directly involved. The only thing he did was write a letter to the president saying, Hitler's going to develop this. You need to get cracking on it. So Einstein was considered a security risk, so they wouldn't let him participate. Besides that, he was a theoretical guy anyway. Okay, so Heisenberg, as I said, deliberately prevented the Nazi nuclear bomb program from succeeding, but they were able to create new cities from nothing. Oak Ridge, Los Alamos, various places around the country. And the people working there, they didn't know what they were working on, except the top-level guys. They just knew, I'm making a screw for something. For what? I don't know. So they wound up manufacturing the three first atomic bombs. The first one was called Trinity. It was the one that we used to test to make sure it would work. And then the next one was Fat Man, the next one was Little Boy. So they set it up to test Trinity from like 20 miles away, inside a bunker with shielding and stuff like that. And Oppenheimer, the guy that had headed the whole project, he knew it's on me. When he detonated the first thing, he quoted one of the Hindu scriptures. He said, I am become death, the destroyer of worlds. It was necessary. It ended the war. That'd be kind of a tough thing to have on you, wouldn't it? Okay, we will stop there for tonight because I think we've gone a little bit further. And I sure hope the camera worked out all right. I'll find out when I get home. Next week, we'll take up right after Chadwick. We'll talk about nuclear chain reactions.